Einstein's coefficient A and B, the big derivation. So Einstein derived an expression because, well, he likes to be in every genre to ever exist, and this one is for lasers. So laser has three quantum processes. So number one quantum process to exist is the stimulated absorption. So stimulated absorption means simply absorption. Like an atom exists, it takes energy from like a photon and it excites to a higher level of existence. That's it. That is absorption. Atom taking a higher level of existence, a higher level of energy by absorbing some energy. Very simple, right? So to properly formulate it, the atom in the ground state, let us consider that as E1, absorbs energy density of an incident radiation and it goes to the excited state E2. Now, let us put that in terms of a expression. So R12. Now R is the rate. Okay, rate of what? Rate of absorption. So it goes, absorption is from lower level to higher level. So from 1 to 2. Okay, and N1. N1 here stands for the number of atoms in energy level 1. So obviously the rate of absorption is going to be proportional to the number of atoms that is present in the energy level 1, right? And to take off this thing, we have to add some constant, proportionality constant, right? And that proportionality constant is the B12, that is Einstein's coefficient. Here, there's also one more factor called rho nu. This rho nu is because absorption is stimulated, which means it is dependent on the energy density of the incident radiation, and rho nu is the energy density of the incident radiation. Now, B12 stands for stimulation. From what? From 1 to 2. Okay, so stimulation, B. And A stands for spontaneous. Okay, now let's go to quantum processes number 2. Quantum process number 2 is called spontaneous emission. Okay, spontaneous emission is when the atom passes from higher energy state E2 to a lower energy E1. Okay, so there's an atom in E2 and it goes to E1 spontaneously. Like there's no energy, there's no external force involved here. That atoms goes from E2 to E1 spontaneously. Okay, and by doing so, this is called a downward transition. Like for the upward transition, right here, this is an upward transition, right? And for an upward transition, there's absorption of energy. So obviously for downward transmission, that means there's a release of energy. So there's a release of energy here, okay? And well, we can create an expression for that too. Again, rate of spontaneous emission. So this is rate and this is from 2 to 1, right? So 2 to 1 and this is spontaneous. So I'm going to put SP. That is proportional to, of course, the number of atoms present in E2, right? And R21 spontaneous is equal to A21 N2, where A21 is that constant. Okay, be good? Yeah. So let us say now formal uh, terms of B12 and BA21. That is all we've seen till now, right? B12 is the probability of absorption transition per unit time. Probability of absorption transition per unit time. And A21 is the probability of spontaneous emission transition per unit time. And of course, you can guess B21 2, right? It's the probability of stimulated emission transition per unit time. So let's see that. The third quantum process, which is the stimulated emission. Okay, stimulated emission. Once again, emission means downward transition, which means it goes from E2 to E1. Okay, there's a downward transition. Now, after this downward transition has occurred, obviously there is a h nu emission. Okay, but the thing here is this downward transition does not happen on its own. There is a stimulating factor, and that's why it's called stimulated emission. So there's a stimulating energy that stimulates this atom to undergo downward transition, and thus producing two energy packets like the same one. Like the one that is stimulating and the one that's emitting will be identical. Okay, so this is what we get. And once again, putting that in expressions, we get R21, this time it's stimulated, is proportional to N2. And whenever the stimulated word comes, stimulated will always be about external energy. And if you have an external energy, of course, your rate is going to be proportional to that energy density of that incident radiation, of that external energy. It's going to be dependent. So we are rho nu. Great stuff. Now R21 stimulated is equal to the proportionality constant we use is B21 and N2 rho nu. That is it. Okay. So now let's come to the main picture. Under thermal equilibrium, there is something that happens. Okay? And that something that happens is the rate of absorption will be equal to the rate of emission. Okay, or the rate of upward transition is equal to rate of downward transition. You can say it as anyway, it means the same. Okay, now we have rate of emission. We have two expressions for that. We have one for spontaneous, one for not spontaneous, where that is stimulated. So we have R21 SP plus R21 ST, but here it's just R12. Okay, so let's write the expressions for that. So this is stimulated, of course, so that is going to be B12 rho nu dependent on N1 is equal to N2. This is spontaneous, so that's going to be A21 plus N2 B21 rho nu. Okay, so now we need to find rho nu. Okay, so I can just take this that side N1, oh, sorry, yeah, N1 B12 minus N2 B21. Can take rho nu as common, N2 A21. Now rho nu is equal to, of course, N2 A21, N1 B12 minus N2 B21. Okay, now there's this expression that I want to compare this to, and that expression is the Boltzmann-Maxwell expression that goes something like 8 pi h nu cube by c cube into e h nu by kBT minus 1. Yeah, really very bad ones. But yeah, there's this expression that Boltzmann Maxwell created for the distribution of atoms. It's really nice, but yeah, it looks complicated. So there's a term called minus 1. And if I want to compare these two, I need that minus 1 term here too. So because of that, I'm going to be dividing by N2 B21. Yeah, I'm going to be dividing that. I'm going to be dividing rho nu by that. Okay, yeah, I was just my brain was glitching. Anyways, N2A21 divided by N2B21 divided by, what is it? Divided by, yeah, N1, N1, B21 divided by N2. Oh wait, it was 1, 2, sorry. B21 minus N2, B21 divided by N2, B21. Okay, so this gets cancelled, this gets cancelled, nothing cancels here. And we are left with this weird expression of A21 by B21 the whole divided by N1 by N2. And yeah, this very weird expression right here. So now let's look at one more thing so that we can compare it to that Boltzmann-Maxwell distribution. Oh shoot, I made a mistake. Sorry, but Boltzmann distribution is something else. Oh, this is not Boltzmann-Maxwell. This is Planck's. I'm sorry, Mr. Planck. May thy rest in peace. Yeah, I'm sorry. Yeah, Boltzmann-Maxwell distribution of atoms was n is equal to n naught e to the power minus en by kBt. Yeah, this is Boltzmann-Maxwell, not that. I'm sorry. Now, when n is equal to 1, we get n1. n1 is equal to n naught e minus e1 kBt. Okay, and when n is equal to 2, we get n2 is equal to n naught e minus e2 by kBt. And with this, we can find this term, n1 by n2, right? We can find n1 by n2. And so, ladies and gentlemen, n1 by n2 is equal to n naught e minus 1 by kBt divided by n naught e minus e2 by kBt. And so n naught gets cancelled. I can take this up, and that will be e2 minus e1 divided by kBt. And e2 minus e1 is nothing but the energy gap difference between e2 and e1. So this difference, and that difference is the exact amount of energy that will be provided by the external energy force. So it is nothing but h nu divided by kBt. Okay, so what do we have now? We have rho nu is equal to A21 by B21 divided by B12 by B21 into EH nu by kBt minus 1. And if you have to compare with Planck's radiation, let's just say that B12 is equal to B21. That is, the probability of absorption transition per unit time is equal to the probability of stimulated emission per unit time. Okay, so that means B12 by B21 is equal to 1. That would give us rho nu is equal to A21 divided by B21 divided by EH nu by kBt minus 1, where this kB here is the Boltzmann constant. Okay, T is the temperature, nu is the frequency, H is Planck's constant, which is 6.626 into 10 to the power minus 34 joules second. And now, anyways, comparing it to the Planck's radiation, I am so sorry, Planck. Yeah, Planck's radiation formula, which he actually is so hard. He works so hard for that. So let's appreciate him. Okay, he said that this is equal to 8 by h nu cube by c cube e h nu by kBt minus 1. So if I compare these both, I will get A21 by B21 by EH nu by kBt minus 1 is equal to 8. 1 second. kBt. Okay, now for the best part of this, cancelling. And we end up with the final expression, A21 by B21 is equal to 8 by h nu cube by c cube. Whew, we're almost done. I'm just gonna do some conclusion parts. Now, what does this conclude? This entire derivation concludes. Number 1, B12 is equal to B21, which I already wrote, which means that the Einstein's coefficient relating absorption and stimulated emission rates are the same. Boom. And then the ratio A21 by B21 is proportional to frequency cube because, well, 8 is a constant, pi is a constant, h is a constant, c is a constant. C is 3 into 10 to the power 8, which is the speed of light. Yeah. So this thing is one of the conclusions from Einstein's coefficient derivation. And also, if A21 by B21 is so much less than 1, then the stimulated emission will be predominant in producing the laser beam. Let me repeat that once again. If A21 by B21 is less than 1, very less than 1, then stimulated emission will be the one that's predominant in producing the laser beam. So that concludes the entire derivation of Einstein's coefficient A and B for laser beam. Thank you.